Recording in progress.
Welcome to all petroleum engineers and students from around the world. And this event that brings together several countries, including Greece, Egypt, Britain, Germany, Yemen, Azerbaijan, and more, in one form of knowledge exchange and mutual development. Our ninth training lecture will be titled as Uncertainty Analysis and Assisted History Matching. This lecture and training is provided by Mr. Hasanain Alsaheib. A brief description about our lecturer experience. Mr. Hasanain is currently working in PP, Iraq, in a production management team as a production forecasting lead engineer. Mr. Hasanain worked as a reservoir management modeling simulation engineer and a project manager in Schlumberger for 11 years. Mr. Hasanain was graduated from University of Baghdad Petroleum Engineering Department in 2011. Mr. Hasanain is also certified project manager with PMP-PMI certificate. We are here hard. We are here delighted to have you, Mr. Hasanain, and very grateful for the information that you will provide in this session. And thank you for your time, and you can start right now.
Okay, thank you. Good afternoon, good evening, everyone. Thank you for joining this lecture. This lecture will be two parts. First part, we'll talk theoretically about what do we mean by uncertainty analysis, what is assisted history matching, when we need it, why we need it. And second, we will talk about, I will take you through an exercise using the software Petrol to show you how to apply these theoretical part on real example, let's say in a demonstration example. Thanks for the introduction. As Haider mentioned, I work currently in British Petroleum in Rumaila field in Basra in Iraq. I'm working since 1 year in this company. My role is lead production forecasting engineer. Before that, I worked for about 11 years in Schlumberger. I took several roles, started with reservoir simulation, then reservoir simulation team lead, and in my about last 1.5 years, I worked as a project manager after obtaining the PMP certificate. Before that, after graduation, I worked for 6 months in Iraqi drilling company as a drilling engineer before I joined Schlumberger. The agenda of today, let's go directly to the topic. I will make introduction to the history matching concept. Then we will compare the traditional classical versus assisted history matching. What is the difference between them? Then we will go through the sensitivity and uncertainty analysis and what is the difference between sensitivity, what is uncertainty, and this will lead us to do assisted history matching approach. And then I will show you a demonstration of how to match the bottom hole flowing pressure on a demo example. Let's first understand the history matching. I believe so this topic based on or should be followed by a fundamental topic, which is the reservoir engineering and simulation. When you work as a reservoir engineer, you will build, or when you work on reservoir modeling part of reservoir engineering, you will make a model to represent your reservoir because you need something to give you indicator of what is going on underneath the surface or in the subsurface. You don't know what is exactly there. You cannot see the reservoir by eye, but you have many indicators will tell you what is going on. Let's keep in mind that all models are wrong. Some of them are useful. I usually say this before I start because when you come as a reservoir engineer and make a model, the other colleague will create another model and you will both give me accurate result from your point of view. It's not a unique solution. The idea here is to represent the subsurface with a model So you say, this is my expected layers, this is the properties distributed among this area, and these are the well location, this is the oil bearing zone, this is the water, this is oil water contact, this is the reservoir pressure, and so on. But you don't know how certain you are. You live with uncertainty. When you will be certain, when you get more data, when you drill new wells, when you do more logs, where you do core, PVT, and so on, you will gather data with time. Whenever you have new data, you have to, what we call it, calibrate your model or history match your model. That means well, let's look at this example. Imagine this is one of your field's wells. So this well is producing with time from this year, let's say 1990 till today. So your model that you will build, which integrate geology, geophysics, petrophysics, and your reservoir engineering approach all together, should be able to reproduce the same amount of liquid or oil at the same time. If your model is able to reproduce the same behavior of your wells, then you can rely on your model. So history matching is the process of adjusting uncertain parameter in the static model to get an approximate match to the simulation historical prediction. As I mentioned, when you have a production and pressure performance in the past, from the beginning of life of the field till today, you have to reproduce these results. So somebody will ask, why should I spend time and effort on something already elapsed, already passed? Because as I mentioned, your model is a combination of multiple uncertain parameters. The geologist will have his or her own imagination to create your static model. The petrophysicist will make the interpretation, and you will distribute the properties from the wells to the reservoir, which will what we call scale-up well log. You will get a sample from one well, and you will consider all your reservoir is behaving similarly in terms of PVT. You will get one core from one well, and you will assume that all the reservoir rock are similar to this sample, which is not accurate, which is not correct. We live with uncertainty and we live with heterogeneity. So the only way to make sure that the model, the reservoir model, is reliable, and you go to your management and say, I can produce tomorrow 1,000 barrel of oil. You cannot say that unless you show them that you can produce what you produced yesterday in reality. If your wells produced yesterday 100 barrel, your model should produce the same amount. If your reservoir pressure 1 year ago is 2000 psi, your model should have the same pressure 1 year ago. So it's the way or the process. Uh, this process, you will make sure your model is accurate and reliable. That's the idea of history matching. You spend efforts and time on something happened in past, but it's the only way that you can rely on to prove that your model will be able to produce future, because it is able to produce history, so it will be able to predict future with uncertain amount of uncertainty. History matching also can involve the adjustment of laboratory measurement data to overcome the inaccuracy inherent in the numerical solution of the fluid flow. As I mentioned, you live with uncertainties. Your fluid, you took one example or one sample and you consider this is your fluid behavior, which is not, should be not the same. Maybe you have compartmentalization, maybe you have a fault, then you have different fluids in different places, which you are not taking into account, and so on. So the idea of history matching, actually the actual problem is you know your input parameters and you put it in a system or equation and you get the output. Let's say the linear equation is ax plus b equal y. So you know your inputs A, X, and B, and you need to get the Y result. If I can do some illustration. There is no annotation here.
You can use the whiteboard on the Zoom. You can use it. I can enable it for you.
There should be annotation, which is faster.
Okay.
There is no annotation. Just try to see look at the options. No problem. If you don't have it, no problem. We can carry on.
There's a button called Notes. I enabled for all participants. You can use it, I guess.
Anyway, no problem. Uh, I think I can use my whiteboard. You still can see the screen, right?
Yes, we can see it.
Okay, okay, okay. Then I will use the whiteboard. Just I need some time to. Okay. So if I want to say AX plus B equal Y, this is a linear equation, simple equation. If you know your input, you know what is your A, what is X variable, what is B, then you will seek the results, which is Y. This is the normal approach. In history matching, you have the opposite. You know Y, but you don't know what is the combination of the equations. So here, you know that you have oil production rate, you know that you have reservoir and well pressure, you know you have water cut and GOR with time, but you don't know how that was produced or how these were produced. So the equation itself, the equation parameter is unknown. You have the system of equations or you have the software and you have the outputs. So it's a reverse or inverse problem. So to define it, it is an inverse problem with non-unique solution. Therefore, it is essential to obtain multiple history matched model to properly quantify forecast uncertainty. The classical history matching way is, let me show you example. So here, I will draw a line, which is represent. This is a simple exercise that I usually use it to show we have water cut and we have time. And your well, this is well water cut, and this is time. So imagine that last year in 2022, this well actually in reality start producing water. So this well start producing well water in 2022. But in your reservoir simulation model, when you create the model, when you drill the wells, when you start the simulation, you found that your well, same well, let's call it P1, start producing in 2023. 2023. What we call the actual production history is, we call it observed. This is the word that we call the actual production of the field or the well. And we call our results from the model calculated. So whenever you see calculated, this is the results from the model. Whenever you see observed or measured, this is the actual. The idea, as I mentioned, you want your model to produce the same amount at the same time of your observed data. So actually this line should be drawn here, should be produced here. Based on your understanding of uncertain parameters, we know if we have mismatch in water production, we have this very famous curve that you should have it in your college, you study it in your college, which we call it KR, relative permeability curve, versus water saturation. So this point here is the SWCR, sorry for rubbish writing because this is not easy to control. So here is your critical water saturation. What I mean by critical water saturation is critical water saturation is the last saturation at which the fluid is immobile. That means the last saturation after which the water will start moving. So whenever you have water, let's say this is point 2. So if your water saturation is equal or less than 20%, the water will not move. Unless you have the saturation increase above 20%, then the water will start moving. So here you are saying that in your model that your water will be late in the production. That means you are assuming a wrong critical water saturation, and because it is late, you are assuming higher than actual. So your curve should be same curve, but should be starting from this point. That means you need less critical water saturation to have the water start moving. So the water will be producing earlier in 2022 instead of 2023. So you need, for example, here, 0.1 water saturation as a critical. By the way, if you have any question during the lecture, you can write down the questions here, and I will go through the answers one by one after the end of the lecture. So please write down here the questions. I will go through them one by one. So here, your critical water saturation should be lower because you took one core sample from one well and you assumed that all your reservoir has the same rock properties, which is not really correct. Then you got mismatch. So what I did now is I changed the value from 0.2 to 0.1 and rerun the model. And this model gave me a new water production profile, which is matching the history. This exercise is manual history matching. That means I change the value. I go to the setting of the inputs and I say instead of 0.2, I need to be 0.1. So this is 0.1 is the new value. Then I rerun the model and I will get the results. So that's what we call it manual or classical history matching. So the classical history matching workflow or steps are you have a static reservoir description, which is the layers, the permeability, porosity, the existing well locations, the rock type, the properties, the facies, all these static properties, we call it static reservoir description because these properties are not changing with time. And this is the duty of geologists to create it, which we call it either geological model or static model. And the reason it is static because it is not changing with time because porosity and permeability will not change with time. Your rock type will not change with time. Your already drilled well location will not change with time. Your surfaces, layers, units will not change with time. So all of them are static. And second reason is you don't have a fluid flow and pressure variance. So it is a static model. Now, once you have the static model, you construct the simulation model that you integrate the static with PVT. So what I need to have in order to have a dynamic model, I need a static model, geological model, and plus I need PVT, initial condition, special core analysis, and the production history. Now, You construct it, you assign the fluid model and rock physics function, which is a cal and PVT. Fluid model is PVT, rock physics function is a special core analysis, which is the relative permeability curve, and second thing is this curve, which is PC versus SW. So this is your capillary pressure, which is capillary forces, and this is your relative permeability curves. These two things or two inputs are special core analysis output. Now, let's see if there is comment. Okay, questions. We will go to the questions later. Okay, so these two things or inputs are the parameters that what we call it is cal. You have other parameter which is the table of pressure, formation volume factor, mu oil, and solution gas oil ratio. And you have table of values. These are PVT. Plus, you have density. You have density of each phase to calculate the fluid volumes in under and in the surface. So these things or these inputs or these parameters will be given by PVT, and these two tables will be given by SCAL, and these two things are integrated with a static model, and it will give you a history match model. So to make a history strategy, you need also to give your production history. What I mean by production history, I mean that I need for each existing well of these wells, I need its production history, which is production rate, pressure, bottom hole flowing pressure, if you have bottom hole flowing pressure, and GOR, water cut, and any given value, any given measurement in time. So if I show you quickly an example of,
Before you go to the example, Mr. Hassanin, there is a question in the chat box if you can answer it.
okay, let's see the question. Okay, I said let's keep the questions at the end, but no problem. Mr. Hamza is asking for the example you show, Mr. Hassan, why we can't say the model, the water saturation note SWI is still lower than SWI, and that's why I delayed mean simulation didn't predicted water saturation accurately. I didn't get the question. You mean it should be SWI, not SWCR? Okay, let's discuss it later after we finish. We can go through this. Now, I was trying to show you the example of observed data, this one. So you should have something similar to this one. You have the well name and you have the time, date and time. Now, if you have it in days and months, so day, month, year, and if you have like well test data, so you can have it in hour, minute, and second, and then you have, for example, here in this example, I have bottom hole pressure, water injection rate, gas production rate, oil production rate, water production rate, and water cut. So I have to list it per date. So at each date, I have this value for each well. So this is injector one. I go down. Some here you have producer three, and the history is from 1999, 1st of January to the 1st January 2005. So you have to give this data to the model. So this is what I mean by history matching uh, or you make history strategy. So your strategy is to reproduce what you give in this table. Now, as I showed you in this example, you have mismatch in water. So you need to define which vector to match. That means I have mismatch in water cut. I have mismatch in bottom hole pressure. I have mismatch in GOR. Each uncertain parameter will give you or will be resulted from uncertain input. So each mismatch will be related to a specific input. That means the water cut is if you have a problem in the start of the match, as you see here, so it's the saturation. Now, if you have the problem in the amount of production, that means you have both the observed and calculated starting at the same time, but the amount that you get is higher. So you have more water rate than the simulation or than the observed. That means your curve here has different inclination. This is the slope of the curve. So if you want more relative permeability at the same saturation, this curve should be in this way. That means at the same saturation here, you have this value of Kr compared to original one, which is this one. So if you have mismatch in the amount of water, you have a problem with the curve itself. If you have mismatch in the time of breakthrough, what we call it breakthrough, you have a problem with the saturation, critical water saturation. Now, again, going back to our slide. Where's the presentation? Okay, going back. So now you will be making a definition of vector to match, which is SWCR in this time. Then you will do parameter screening. Then that means you will change this value. It was 0.2. You say, let's make it 0.15. Then you run the model. You didn't get good match. Then you change it again. 0.1. You run the model until you reach to the result that your history data is matching your model. Then you move to accept history match and move to the second stage, which is a prediction. This is manually changing. That's what we call it a classical history matching. Now let's define uncertainty and risk. Uncertainty is the lack of knowledge or information on a state that makes it impossible to exactly predict the future outcome of process. Let's take an example. When you want to drill a well, a reservoir, you know based on your current amount of knowledge and data that you have 40% chance that this well will be dry, will not produce oil. So this 40% is what we call it uncertainty. Now let's look at risk. Risk is the impact or the probability of the chosen action to cause a loss. So now it is related to loss or to, let's say it's part of economics. Now here we are talking about technical. Technically, you will drill a well, 40% of the time this well will not produce oil. This is just uncertainty. But when you drill a well and this well is not producing well, is not a producer, that means you will lose the amount that you spend on drilling, which is, let's say, $12 million in the exploratory drilling cost. So when you say uncertainty, you are uncertain or you are not sure about the technical result. When you are at risk, you are economically not safe. So you have risk of losing money, which nobody want to lose money. The idea is to develop the field to have a gain, not loss. So this is the uncertainty and risk. Now, if we look at our life cycle of the field development, we have uncertainty in each part of the development. You have the in exploration, of course, it's the highest uncertain area. You have risk of non-discovery, risk of non-development. Imagine that you spend amount of money to do exploration to a field, you get the 2D and 3D seismic, you spend the money, you go to the processing center, you do the modeling, and you found out that it is not economically valuable produce. So this is a risk. That means you don't know about your traps, seals, salts, charge volume, structure, closure, hydrocarbon type, and so on. In the development part of the reservoir, once you explored the field and you found there is oil, you will move to the development. Now, in the development, you also have a problem, which is risk of error in reservoir model. When you do a model and you expect to produce, like, let's say, this X amount of millions of barrels, you are not sure because you don't know what is your reserve, how much reserve you have. It's not you don't know, it's you are not certain, uncertain again, or your drainage volume, structure, your contact, connectivity, the net to gross, the compartmentalization, which is if there is fault, if there is different properties across different areas, well productivity, drive mechanism, number of wells. All of these are uncertainty. You are living again with uncertainty. Now, you move to the production. In the production, you have risk of suboptimal FDP. You have a risk of drilling dry well. You have a risk of missing the target. Missing the target means, let me show you quickly if it's not clear that let's imagine that you have a thin layer, tight reservoir, and you are drilling a directional well. So when you drill a directional well, you need to make sure that your well is passing through this layer, not outside and not beneath. Otherwise, it's dry. It's not producer. And in order to get that, we usually do what we call it, just for your information, geosteering. So geosteering is they insert a logging tools, and the borehole geologist will sit on the same time in real time, getting the data from the rig, doing interpretation, and making sure that you are going through the correct direction and depth. So that means the well will keep going through the target. This is the target, not out above, not below. So here is the missing target. And this is again due to saturation distribution and full well locations, with efficiency, connectivity, and so on. So all these parameters, all in all your development or all life cycle, you have uncertainty. Now, somebody could ask a question. Now, when I have the most accurate reservoir simulation model? The most accurate reservoir simulation model, we will have it at which time? Exploration, development, or production? The answer is we will have it at the abandonment. That means once you have produced all your reserve, once you have developed the field 100% and you closed this field, now you have the 100% accuracy that you produce this amount and you can build a model representing your reservoir. Any step before the abandonment is not 100% accurate model, but it has some accuracy based on the amount of data that you are getting. Every day you have new data, you are reducing your uncertainty. That's why I told you in the beginning, all models are wrong, some of them are useful. The only model which is not wrong is at the abandonment of the field, which is not the good time to make the model. We already closed the field. The source of uncertainty, as I mentioned, now you are making a reservoir model and you want to say that I will produce this amount of oil next year. This model is consist of seismic data. When you have as I believe you all aware of that you have the seismic track and geophones distributed in 2D or 3D, then there will be a shock. The track will hit the floor, the ground, the area, and the waves will be going down to the earth and reflected to these receivers. Then They will go to the processing team. They will remove the noise. They will make the interpretation, as you can see here. They will give you indicator that this is a formation, this is a dome, so this could be a formation. Then you go to drilling a new well, you go to well logs, you do interpretation, you expect from what we call it formation evaluation, or we call it triple combo if you heard about this term. That means you have the caliber, the gamma ray, the resistivity, the neutron, the density. All these logs will be integrated to give you indicator that this is oil bearing zone, this is water zone, this is not reservoir rock, and so on. Then you have the sample, you take it from one of the wells and you make special core analysis and you come out with this table, which is relative permeability table. You take a sample from one of the wells and you make it in the lab, you analyze it in the lab and you get the fluid PVT properties, which is BO, mu, RS, bubble point pressure, and so on. All of these are uncertain because you are looking at one point or several points representing several kilometers. Let's say one of the fields that we have, the length is 40 kilometer, the width is 10 kilometer. Imagine how you can represent one sample from one well to represent all this area. For sure, it's uncertainty. But again, once you carry on developing the field, you will get more data, you will calibrate the model until you have a certain or more certainty. So all of these are uncertainty, as I mentioned. Now, let's frame the uncertainty. Here is the life cycle from exploration to maturity. In the exploration, your cash flow is negative. That means you are only spending because you are not producing, you are not getting money. But there is something we call it value of information. The value of information that you spend money here will be reflected later in your gain. So during exploration, you are spending. During delineation, you are spending. Then, when you start the development, you start getting the cash flow, which is a plus. Now you are getting money. But once you have this curve, you need to minimize it. What I mean by minimize it, you need to spend less amount of money, which is the white curve, not the gray curve. You need to spend less and you need to produce more because, as you know, in optimization is higher gain with minimum loss. You don't want to spend more than you want. You want to gain more than you expect. But unless you do a very accurate risk assessment, your curve will be the gray line. So your well or your reservoir will be abandoned early. You will spend more at the beginning. But if you do risk assessment, uncertainty analysis in a very good way, you will spend less and you will gain more. So this is the idea of uncertainty with the life cycle. Now, if you talk about course, when we say exploration to majority, it's not about only about reservoir simulation. It's all field development plan. But what we are interested here is the reservoir simulation part, which is part of the field development plan. So here, one of the good examples is to represent your field with a model, as I mentioned before, and you predict your future performance. But if you have single scenario, you will have one output. If you have multiple scenarios, you will have more, let's say, more vision on what if scenario. If my fault, what I mean by fault is the rupture in the rock due to tectonic forces. If this fault is 100% sealing fault, so the fluid here will not cross through this fault to the area here. Or if I inject here and this fault is sealing fault, the injected fluid will not support the pressure here. Again, let's do another realization that this fault is minor. Let's ignore it. This fault is major. Let's take it. This fault is partially sealing. That means it is allowing the fluid to go through the fault, but it's not 100%. Let me draw quickly some example to show you what I mean. Imagine that you have this layer, and this is the fault. So if your layer has been moved like this, so this is becoming sealing fault, that the fluid here will not flow here. Okay. In other example, you have partially sealing fault, that the layer has been moved, but it's not totally moved. That means this is, let's say, sandstone, and this is sandstone, and this is, for example, shell. So here there is no movement, but here there is movement, but it is partially sealing. But in this area, it's 100% sealing. That's what I mean by sealing and partially sealing, and I will show it to you in the example in the exercise. Now, once you build all your inputs, as I mentioned here, integrated in one model, start producing, you will observe this one. Usually in the simulation, the dot line represent the observed. What I mean by the observed again? The observed is the measured parameters, or the measured values. That means the actual values from the field. What about the green line? This is the calculated. This is the result of the model. And as I mentioned, because the model has hundreds of uncertainties, it might not give you the same behavior. Here, the example is bottom hole pressure for prod 1, prod 2, prod 3, prod 4, and producer. I have 5 wells. One of them has good match, but 4 of them has bad match. When I have good match, when the green line pass almost over the dotted line. Before that, your model is uncertain, is not matched. Once it is not matched, it's not accurate. Once it's not accurate, you cannot carry forward and do the development of the field in the future. Now, once you observe that your model has mismatch in this parameter, which is bottom hole pressure, you need to do sensitivity analysis. Let's define sensitivity. The variable-based sensitivity of the given model is determined by successfully selecting one variable at a time from a set of all uncertain variables. Here is one example. Let's go back to this example. Sorry. Let's go back to this example. You know that you have mismatch in water cut and mismatch in time of breakthrough. So yet what you will say, I suspect SWCR, critical water saturation. How much you suspect it? I suspect this between 0.2 and 0.01 or 5. So this is the range of uncertainty. I don't know which value between 0.2, 20% and 5% is the most accurate value that will give me match. So this is variable. The variable is SWCR. Let's take another example. For example, let's say relative permeability, or let's say aquifer. The aquifer volume is, let's say I said it's 1,000 barrel, but I'm not sure, is it 1,000 barrel or 1 million barrel? Because when you drill and you develop the field, you don't look at the aquifer. The aquifer is a water reservoir, either beside or beneath your reservoir. Nobody spent time and money to explore the aquifer because it's water. But aquifer is playing a, let's say, a key impact on the reservoir because it's the area where you have a pressure support to the reservoir. So this is another parameter. So this is uncertain parameter number 1. This is uncertain parameter number 2. Now, what you need to do is you need to tell the simulator that I suspect this parameter, which I showed you now, and I want you to examine, making a loop and changing this parameter once at a time, and tell me which of these parameters are impacting the result, which of them is not impacting the result. So this is the idea of sensitivity. What the simulation will do, you will list here, as you can see, tens of uncertain parameters. That means, let's read it. The fault transmissibility, the transmissibility multiplier, the pore volume, I don't know what is this, net gross or what. For example, critical gas saturation, aquifer, extended radius, many inputs that you suspect, you are not sure. What you tell the model, check each one at a time and tell me the impact. Why it is sensitivity? That means, is the model sensitive to this change of this parameter? That means when I change the SWCR between 0.2 and 0.05, is it impacting the result? Is the model sensitive to this impact or not? That's the idea of sensitivity. So you define which parameter is impacting, and I say this parameter or the model is sensitive to this parameter, but it is not sensitive to this parameter. Why? Because whatever I change the value, there is no impact here. And by the way, this curve or this graph, we call it tornado plot. It's look like tornado. That means it give you either positive or negative impact. But the idea, it is impacting. So you do what we call it cutoff, which is the next step. First step is you understand these parameters are impacting your reservoir. These parameters are not impacting. So you will ignore this one. You will not spend time on changing these values because it will not give you any impact. You spend time on adjusting and changing these parameters because your model is sensitive to that. Once you define which parameter is sensitive, which parameter is not, then you need to come up with what we call it uncertainty. So you say, I know the critical water saturation is sensitive parameter, but I'm not certain how much I should change to get the result. Let's look at the uncertainty terminologies that we will use. When I say range, I told you now in this exercise, this parameter is SWCR, and the range is from 0.2 to 0.05. So this is the range. It refers to the minimum and maximum value of in the distribution. That means your critical water saturation between 0.05 to 0.2. This is your range of uncertainty. The expected value of discrete variable x is the same as the arithmetic mean. There is another term, which is the standard deviation. The standard deviation is the measure of how much sample value differ on average from the mean value. That means how much it is differing on left or right from the mean of the value. We have another term, which is the probability density function. The probability density function is the statistical function that depict all the possible value and likelihood that a random variable can take into a given range. That means if you give a range to this parameter, it will tell you 80% of, we have a probability of 80% that X will be 150 or less. This is the probability density function. The cumulative distribution function which is opposite to this one. So it will be, the curve will be in this shape, which I will show it here. Based on these terminologies, we have this curve, which will give you indicator of how much probability you have, percentage based on your known data or your known parameters. For example, if we are looking at reserve, and by the way, oil in place is different from reserve. Reserve is the amount of fluid or oil that you are able to produce under your current possibilities, current tools, functions, and money. But your oil initially in place is the total amount of hydrocarbon in the reservoir. Now, if you are using only depletion, you will, let's say, you will produce 30% of oil in place. That means your proven reserve is 30%. While if you use water injection, you have more money, you have good plan to inject water, you will increase your production to 50%. So this is your reserve now, 50%. Now, if you have ability to do enhanced oil recovery, CO2 injection, water alternating gas, whatever, then you will have more recoverable oil, let's say 70%. So reserve is changing based on your ability to produce, while oil in place is fixed, that this is the amount of hydrocarbon in place. And we have three terminologies that we use it usually, and SPE standard call it, which is P90, P50, P10. The letter P is probability. So when you hear P90, P50, P10, that means probability. This is very common use terminology in every and each company. And not only in reserve, in every uncertain parameter, they will tell you what is your P50. That means what is the 50% probability that you are certain. So if you say here P90, P90 is the proven. If you look at the curve, if you take 90 and touch the curve and go down, you have less reserve. While P50 is the proven and probable, so you have more reserve. While proven, probable, and possible will give you highest reserve. But as long as you have less uncertainty, less probability, you have high risk. Okay, you say I will have 400 billion barrel, but let's say here 400 million barrel, here 200 million barrel, 100 million barrel. You will have 100 million barrel, but you have only 10% sure that you have 400 million. So it is a combination between your certainty level and your risk. And this is very known terminology proven when you have a successful pilot project and you have infrastructure in place. That means you have drilled wells, you got oil, you have built your surface facilities, so you know this amount of production, you are able to produce it. But probable, you know the reserve. Reserve appear to be productive based on well-logged characteristics. However, core data or definitive test are lack of classify reservoir as proven. You know, you did analysis, you did some measurement, like you have exploration well, and you did well log, and you did formation evaluation, but you still didn't take a core sample, you didn't do a PVT. So you have a probability of having fluid, but you are not still sure like proven. What about possible is the highest risk? There is reserve. You know there is reserve in the rock. Fluid and reservoir characteristics that create reasonable doubt that the project will be commercial. So you only know you have indicator. Let's say you did seismic and you expect there is a reserve and there is a formation with oil, but you have very high uncertainty with high risk, which is what we call it possible. Now, I showed you the sample and the range. This is the parameter, and this is the range. Now I want to take sample. For example, I want to tell the simulator to try value at a time between 0.2 and 0.05. So I need to define how I will do my sampling method. In the simulators and in the tools that currently available, there are several sampling methods. The first one is what we call it Monte Carlo sampler. Monte Carlo sampler is a random stochastic sampling method. That means you say, I have a range from 1 to 10, and I want to take 5 samples. It might take 1, 3, 7, 9, 10. It might take 1, 2, 4, 7, 10. It's randomly stochastic method. So it will take samples in a random way. You have the second method, which is equal spacing sampler. Equal spacing sampler, from the term, from the name, it will divide your range into equally spaced values. That means if you have a range from 0 to 20 and you take 5 samples, it will equally divide the range into 5 parts or partitions. So it will take 0, 5, 10, 15, 20. Or you have CSV sampler. CSV stand for comma separated value, which is you open a, let's say, notepad file, and you list your samples that you say, I want to take 0.2, 0.3, 0.4, 0.45, 0.5. So you list the variables and you put a comma between each term. That's why they call it comma separated value. And there is another one, which is Blackett-Borman. Blackett-Borman, if you have 3 parameters, so you take the same parameter, then you take minus one value minus, maybe you take one value above, one value minus, or opposite. So you make like different combination, or this sampling method will make different combination of 3 parameters to take a sampler from. The important part that we usually use, 2 things that I usually use, or we usually use in reservoir engineering and simulation, is the equal spacing and the Monte Carlo, but we will explain something integrated with Monte Carlo. So as I mentioned, Monte Carlo is a stochastic method that samples the variables randomly from their input distribution. Let's say you have this uh, combination of 2 variables, so it will randomly take values. If you look at this range here, it didn't take from this horizontal section, it didn't take from this vertical level. So there is no value taken from this range, no value taken from this range, no value taken from this range, and this one as well. What they said, they have integrated another method, which is Latin hypercube sampler. What is Latin hypercube sampler? It will be, again, randomly distribution, but before it will randomly select the values, it will divide your range into equal spacing sub-range, and it will take random value from each. Let me draw it for more visibility or explanation. Let's say this is your range. So if you are saying only Monte Carlo, it might take one sample here, one sample here, one sample here, one sample here, and 5. We have 5 samples. This is the randomly stochastic method, which is Monte Carlo. If you say with Latin hypercube, what will happen? Latin hypercube will divide equally your range into 5 area, and then again Monte Carlo will randomly select from each part. One is here, one is here, maybe one is here, one is here, and one is here. So you make sure that you covered all the range. However, within each sub-range, it will be randomly selecting maybe here, maybe here, maybe here. But at least you make sure that you covered all the value, let's say from 1 to 10. So this is the Latin hypercube with Monte Carlo. Now, once you finished, you will your sampling, you run your model, it will give you what I showed you before, P10, P50, P90. P10, P50, P90, which is the probability of uncertainty. That means you are either P10, only 10% certain, or you are 90% certain. But your 90% certain will give you less value than your 10% certain, of course, because this is high risk, this is low risk. Now, we need to do this one in automated method. It is not really feasible and not really user-friendly to have, like, let's say 10, 15 parameter, and each of them have 10 samples, and you change them manually. Then you go to the simulator and change one value and run the model. You need it automatically in the tool. So we have what we call it assisted history matching, and this is based on the root mean square of the 1 over n, which is the number of points from 1 to the n, which is the total number of points, which is the square difference between the simulation minus observed. So this equation is incorporated inside the software that will work on taking the samples, compare it to the observed, and give you the best selection from the range. Again, it will not give you any value unless you give it a range, and I will show you in the example. If you tell water saturation from 0.2 to 0.3, it will take the values between 0.2 and 0.3. It will not go above 0.3 or below 0.2. So you control it, but it will help you to quickly and let's say automatically select and run the samples within this range, but you have to define the range. And this is the typical workflow. You have your task, you build your base case, you know what is the uncertain parameter. That means you say my uncertainty in oil water contact depth, in the fault transmissibility, in the aquifer volume, in the water cut, in the critical water saturation, and in the relative permeability, and so on. Then you did the sensitivity. That means you defined which parameter is affecting the model or the model is sensitive to, which parameter is not. Then you did the uncertainty to come up with the 3 cases if you want to, which is P10, P50, P90. Then you do the evaluation strategy, which is what I'm going to explain in next slides, which will make a samples random or equal spacing or whatever the method that you selected, compare the simulation with the observed until you reach the accepted solution. Then you move to prediction, which is the development of the field. As I mentioned before, this is the objective function. So the objective function is you want to minimize the difference between the calculated and the observed. How to do that? You have the initial input. It will go and select a range or a value from the range, what we call it parent. It will do a recombination. It will generate output. It will compare it to the observed. Is it matching? Okay, we will accept. If not, it will go again and change the loop. In order to show to you in a very simple example, the evolution strategy is based on Darwin evolution theory. So here we will say this is our first generation. So imagine that you have 4 parameters, which is parent A, parent B, C, and D. So the parent A is strongest, parent B is normal, parent C is weakest, parent D is strong. And you know, from strongest and normal, the child will be strong. From weakest and strong, the child will be weak. What Darwin says, over time and generations, the weak child will be vanish and weakest as well. And it will be second generation will be replacing the strong child with the weak parent. So your second generation, all your parents are either normal or strong. Your first generation was weakest and weak. And hence you have better result, which is all your children will be strong. Before it was weak and strong. So this is the idea of Darwin. Same thing in the evolution strategy. That means you know your observed data. You know the range of uncertainty. It will take value from the range. Compare it to this observed. Is it giving you better result? No. Then change the variable. Go again, take another variable until you get the best match in our terminology. So here is the objective function. You start with very big mismatch. Your objective function is to minimize, as I showed here in this example, here, to minimize the difference between calculated and observed. So here, it is start with very big gap or very big difference It will keep changing. These are generations. You see generation 1, 2, 3. So it will try to keep minimizing the difference with time. Sometime it will check or take wrong sample. It will disperse again. So there is diversion and conversion until sometime it has a stagnation. It is like stagnated with specific range. Then it will take another range. It will be destabilized until you will reach to the best match, which is the best sample from the range that matching your observed data. And here is the result that you will see. I will show you in the example. Initially, this is the curve, the base case, which is the red color, and the green is the observed. So you have mismatch. Once you have changed these input parameter, it will run and run and run. It will make hundreds of runs, depend on how many runs you want to have, until your curve will be matching your observed. Then you say, I have match. Once you have match, then you can carry on to the prediction. Let's look at the questions before I show you the example in Petrol. So, Mr. Hamza, if you are still here. Can you unmute?
Please, Mr. Hamza, if you have any question, write it in the chat box or raise your hand so I
Just
can.
I want to understand the question correctly.
Okay.
Yes.
You can speak now, Mr. Hamza.
Hello.
Hello, Said.
Hello. شلونك حسن?
Hello.
How are you? I'm doing good. My question was regarding the example you showed of critical water saturation. It's very reasonable that critical water saturation has uncertain value, but I was trying to find another reason, which I said maybe simulation did not simulate water saturation accurately, so it is still lower than 0.2.
ممكن, of course, yes, might be. So here the problem with your PC, this is the minimum SWI that you gave. So you
Yes.
need to check the PC, because in the oil zone, this is your SWI. In the water zone, this is your SWI, which is 100%. And here, between in the transition zone, this is the transition zone. So this is your capillary. So maybe you have, or you missed, or you didn't have good result of capillary pressure forces. So your initial water saturation may be less, maybe here. That could be another example, or could be more based on your results. Of course, this is one of the reasons. I showed this as a simple example. It might be one of the reasons, but it never be one. And history matching, as I mentioned, it's not unique solution. That means if you say 5 plus 5 is equal 10, you know 10 is your result, but you don't know x and y. So I say 5 plus 5 is equal 10. And Hamza will say no, 9 plus 1. Other one will say no, 5 by 2. So all of us has correct vision or correct input to the results, but it is not unique. But should be reasonable. That means you cannot make your SWCR less than SWI, for example. Cannot. Right, Mr. Hamza?
Yeah, correct.
SWI should be always less than or equal as WCR. Otherwise, it's not physically accepted. And I don't recommend you keep your SWI equal to SWCR, because once you have water, it will flow. You need to have one value of SWI where there is initial or irreducible water, then you have SWCR, then the water will start moving. I hope
And
I answered.
the process is different. SWI is due to water being displaced. SWCR is water is displacing.
Yes, correct.
Other question, Mr. Hassan. The history match steps you explained, for example, sensitivity analysis, and the distribution, you show the normal distribution curve and how to get the cumulative probabilistics. I didn't know exactly what are the steps and what is the input to the simulation.
I
Which
will
one
I will do it
first?
now in
Yeah.
in exercise. I will do it in
Okay.
details.
Thank
I
you
will
very much.
show it now. Thank you. If somebody is asking about the attendance link, this is the link to register and attend. And now I will show you a simple example of how to do assisted history matching using Petrol. You still can see, I believe, yes. So here is a simple example. I have this reservoir. I have 4 blocks divided by 3 faults. So there are 3 faults in this model, which make the model divided into 4 blocks. And as you can see, I have 4 wells drilled in the central block, right one, and have 1 well drilled in the west flank. Now, I have the simulation. I don't think I have run this one. Let me check. Now, I want to have a look at the performance. One more thing is, this field is connected, is the geologist believes that the central block of this model is connected to aquifer. This is the color of the aquifer, and this aquifer size is 10 million barrel. So this is your model, and the geologist told you based on their observation that this model is connected to aquifer from south side. That means this aquifer is edge aquifer with 10 million barrel, the volume of the aquifer. And you know there is a fault here, which it might be sealing fault, it might be partially sealing fault. So you don't know if there is a flow across this fault between this block and this block or not. Now, if we look at the results, if we want to see the simulation results, let's see if I have run this one. Okay, it is not run. So let's run the model. Okay, the model is run. Mr. Haider, people are asking for the link.
All right, I'll send it.
I think it's here, but maybe they disconnected. So please send it again. Okay, so I have run the model. I have run the model. Let's look at the result from simulation, result charting. I want to see the case, rod, bottom hole, pressure. My example is on pressure. So as you can see here, the dotted line here is the production history. That means this well started producing in 2003 until 2013. This is the pressure. While my model that I have created, this model that I have created, it gave me lower pressure. Now, if you have lower pressure, one of the affecting parameters is the aquifer, because let me show here something quickly. This is the aquifer. How do you know the impact of the aquifer? If you have this pressure with time, if your pressure with time is in this curve, so that means dP over dt is equal what? Equal 0. When there is no change in pressure with time, whatever amount of production you are producing, that means you have strong aquifer. So you have a pressure support. So whatever pressure is lost, you are getting back from aquifer. What they call it, this one, steady state. If your pressure with time in this way, so changing of pressure with time is what is constant.
Semi-steady state.
So this is what we call it pseudo steady state. Yes, pseudo steady state. And if your pressure is this shape with time, that means your dP over dt is what now? Is function of position and time. Here, it's a transient flow. So based on these indicators, you can imagine what is your pressure support. So if we have aquifer now and we gave it smaller value, that means we are giving the reservoir less energy than expected. So we need to check that. Second thing, here, from this window, you have a fault here. So maybe you are losing a pressure from this block to this block, and this fault is sealing, or opposite, and this block is sealing. So you need to test your fault transmissibility. So now we will look at three parameters: the fault transmissibility, the aquifer volume, and the aquifer productivity index. What I mean by aquifer productivity index is when the pressure drop by 1 psi in the reservoir, how many barrels of water will be going to the reservoir? So that means barrel per day per psi. So to do this assisted history matching, we will do first uncertainty. To do uncertainty, you will need to define your objective function. So my objective function here is a tool here called objective function. This one, if you can see this one, click on that and you say, I want to make objective function of history matching. Your objective function is to minimize the difference between calculated and observed. You have your observed data, which is the production history that I showed you: pressure, oil rate, water cut with time. So you have to drop it here, and you need to bring your base case here. That's the parameters. What I need to do is to tell the simulator that these are the parameters that I want to play with, or I want to minimize the difference between them: pressure, gas, oil, water, tubing head, whatever inputs you have. Okay. Now, if we move to production data tab, now this is the data mapping. In the production data map, here you will define the what we call it, the value that your measurement error. So we will start with these four parameters one by one. First one is bottom hole flowing pressure. So for the bottom hole flowing pressure, I want to change the measurement error here, this measurement error, to be 20 psi. So here measurement error is 20. That means I need the delta between calculated and observed in each well no more than 20 psi. Okay, now I will move to the second one, gas. For the gas, I want the measurement error to be no more than 50 MSCF per day. So it is 50. Third, oil. I want the mismatch in oil to be no more than 10 MBD. So I want my prediction between calculated and observed within 10 MBD. You see, I highlight all of them and give one value instead of write it 5 times. That's the idea. Last one is water. For the water, I don't have tubing head, so I will not look at it. For water, I want it to be a percentage of 5%. So the error percent here, I will highlight it and click on percentage, and I will say 5. That means I don't want the mismatch to be in volume. I want it to be in ratio. That means instead of I say I don't want the match to be within 10 MBD water, I say 5%. So it depends on what you want to do. And the click apply to selection only, because if you give this percentage and you don't select this one, it will be applied to all parameters, which is oil, pressure, and water and gas. It has been applied. So it calculated the difference, which is 7 MBD. You said 5%, and the simulator calculated the number. So now if I deselect all, now I have 20 for the pressure, the bottom hole pressure, the gas 50, the oil 10, and tubing head, I didn't look at it, and or let me just remove it from here. I don't want it. And I have the water, which is 7.6. So what I did now, I have set my objective function. Okay, click OK. Once you clicked OK, it will be saved here, named objective function 1. Now I will go to the tool called uncertainty analysis, uncertainty and optimization. Just want to get this out. Simulation, this one, uncertainty and optimization, this tool, the yellow histogram. Now, in uncertainty, what I need to do, I need to bring my base case, which has mismatch. This is my base case. Okay, so I brought my base case. And I need to select the task. I told you, we do first sensitivity. What we mean by sensitivity, we need to check which parameter is sensitive to the model, or the model is sensitive to this parameter, which is not sensitive to. So I don't spend time on changing non-sensitive parameter. So sensitivity. Okay. Now I will do edit workflow. I don't want to change all these input. You can keep it, no problem, but just to reduce the time of loop. So I will keep the 3D model. Okay. I will remove make contact, make horizon, geometrical modeling, make fluid, make rock, because I will not change anything in these tools. If you are changing anything, you can keep it. Here, I'm not changing, so I will remove it. It is not deleting. You say it to the simulator that skip these. That means I will keep PVT as it is. I will keep my geometrical property as it is. I will keep my special core analysis as it is. But I need to add, it is not here, the fault transmissibility. So I will search for a tool or process called fault transmissibility, fault analysis. Fault analysis. This is fault analysis. So I select it and click on this blue arrow here. It is here. I will move it up to be with the 3D model before the aquifer. Now I close the workflow. Okay. I haven't done anything. I have just listed the things that I might change. That's it. Now let's go to the fault. Double click, it will open the process. You have a fault called fault 1, and the value in this fault is 1. That means there is 100% transmissibility between the western and the central block. I showed you in the window that there are 4 wells. I cannot show it now. I will show it here. This one. Here. You have a fault here, and you have 4 wells here and 1 well here. When you say fault transmissibility is 1, that means you say it is fully transparent between these 2 blocks. But I suspect that. So instead of giving value in the manual history matching, what do you say? Let's make it 0. Click OK, run the model. No, let's make it 0.5. Click OK, run the model. No, let's make it 0.7. But I don't want to do this manually. I want it to be automated. So either I right click and say auto variable, or I write $sign, which is shift and F and number 4, and I say FLT, and I name it the name I like, FLT1. That means fault number 1. When I say $sign fault 1, the simulator or the software will understand this as a variable. So now it will write it to me here as a variable. يسألون على رابط الحضور أستاذ هاي. زين. So this is a variable.
It's nice.
Now, this is one variable. Second variable, I am doubting the aquifer volume. So what I will say, double click on aquifer, and I have this aquifer. Initially, the geologists believe the size of the aquifer is 10 million. I say no, it is more, because the pressure I got is less than the observed. That means I need more energy. So what I say, $sign aquifer volume. I will name it the name that I like. Any name you like. Just you need to know which name means what. That's it. And your aquifer productivity index. That means how many barrels of water will enter to the reservoir when there is 1 psi drop in the reservoir due to production. This is initially 5. I will say, let's make it as uncertain parameter. So how many parameters now I have? I have 1 fault transmissibility and 2 in aquifer. So in total, I have 3 uncertain parameters. Now, I define the parameters, but I didn't say from which value to which value. So I will move to variables, and it will give me a list of variables that I have created, and what their initial value, and what are the minimum and maximum value that I want. The initial value in default was 1, and I want to check between 0 and 1. I want this range. You remember the range? This is the range. This is the range. I want it between 0 and 1, default. And productivity index. I want the range between 5 barrel and 500 barrel per drop in PSI. The aquifer volume, initially 10 to 7. I will say 1E to 7. The minimum, maximum, 1E to 11. Between 7 and 11. The amount of, what I mean by 10 to 11 is 100 million. 10 to 7 is 10 million, 1 to 7. Instead of write it in zeros, Petrol can understand 1E7. That means 70, 111, 11 zeros. Okay. That is the ranges. So I have set my range. I have set my uncertain parameter, and I have defined the minimum and maximum range. Now we go to sensitivity. Now you said I need the sample from 0 to 1, but you didn't tell the software how many samples between 0 and 1, how many samples between 5 and 500, and what is the method of sampling. Is it Monte Carlo, equal spacing, Latin hypercube? What is it? So you move to sensitivity, you define the number of samples. Here, if I say 5, and I have 3 variables, that means the total number of runs will be 5 by 3, 15. Because it will take, let's see. And the method, either Monte Carlo or equal spacing, I will say equal spacing. So it will take the fault transmissibility once is 0, this is 1 run, 0.25, 5, 0.5, 0.75, 1. Then it will move to aquifer, 5, 128, 252, and so on. Then it will move to volume. Each of these parameters will be run at a time. That's what I call it sensitivity. Each parameter will be run at a time. Why I run independent parameters? I want to see the model is sensitive to each of them or not. Okay. Now Once I finished, I will say test. If test is okay, I will say run. And look at here, the cases is only one case, which is base case. Now I will say run. It will run 15 times. You see here in the window, 15 times. And then it will, I believe I got error because I haven't limited the number of runs. It will give me error. No problem. I will fix it. Because I have limited license and it is running at a time, all at same time, I need to change the setting. Sorry for that. But this is the idea. It's running. It has run 15 times. I will show you again. You see, it has run. It has make three folders, each folder called by the variable name that I set, and each of them has 5 runs. But why 5 runs? Because I gave range of 5 to each variable. Let me fix the problem, and we rerun again. Project setting. Not here. Now it will run one by one. Once this finish, it will run the second. Before it was running all together because there is one license, so it will run once at a time. Now it is running normally. No errors. Imagine that you have a real field and each run will take, let's say, 5-6 hours, and you have 20 uncertain parameter, and each one you have range of 10 samples. So you need to keep it running for 1 week, 10 days. Instead of you change one value at a time, you set your range, you set your samples, and you set your sampling method, and you run it and leave it. After it finish, you will come and look at the result. But you need to make sure you don't have errors as I did now in the setting. So you leave it at working, and once it's finished, you come and analyze the results. And I will show you now the results. Now it has run another 15. So you see now from 16 to 30, run is finished. And here is another folder, which is which was successful. Okay. Now I want to see which parameter is impacting, which parameter is not. So what I do, I go to tornado plot and say objective function. How many parameters I have set? I have set 3. Aquifer volume, fault transmissibility, and aquifer productivity index. And I told you in the slides, we will do cutoff. We will take the parameters that impacting the model and we will ignore the one that not impacting. As you can see here, there is no change in the objective function. Although we changed the aquifer productivity index between 5 and 500, while there is change in the fault transmissibility and there is more change in the aquifer volume. So that will tell me that these two things or these two parameters, the model is sensitive of changing these, but it is not sensitive. So you don't need to spend time changing this one anymore. So the next step is I will go to uncertainty and optimization, create a new because the existing one is just finished, which is the sensitivity. Create a new. Now I will make my task is optimization, which is the assisted history matching. Optimization. Now I will go to variables. Which one is not impacting AI? I will ignore it, disable it. Why? Because I don't want to spend time simulating parameter that's not impacting. So once I set it as disabled, it is now has no range. It is disabled. Now you keep working on these two. Moving to optimizer. Before it was sensitivity. Now because you changed the task, it became optimizer. In the optimizer, here you do your history matching. So the method is evolution strategy that I have explained to you. The maximum iterations, let's say 50. So it will make 50 runs. Your objective is, because history matching, you want to minimize the difference. Minimize. Okay. Here, number of children, number of samples, for example. You can say what is your mutation standard deviation, and so on. So once you test, there is problem all variable defined in this comment are inactive. Okay. I haven't validated the base case. One second. Minimize. 50. Just setting, no problem. Okay. I have to change. I'm sorry. I have to change the type to control. Uncertain and uncertainty and sensitivity. Now, in assisted history matching, this should be control. Error validating variable 1. Control. Yes, should be control. And start with 0 point, let's say in the middle, 0.5. Let's start in the middle, 1E9. And test. Now test is okay. So I missed to tell you that when you do optimization, you disable the unwanted parameter and you change the type from uncertain to control to other. And now once you say control, you need to start from a point. Before we say minimum and maximum. Now you need to give the start point, which usually I give it from the middle. No problem. You can recording stop. Okay. And now once you set up this and test, the test is okay. Once you click run, it will run 50 times. Just to save your time, I have run it before and saved it. So I will show it to you now. And I will show you the 50 runs and the results. So after you run it, you will have a new folder. And this new folder will be called optimization. And it will have 50 runs, as you can see here. And it will open this output sheet. What this output sheet will tell you that it has run 50 iterations. And in each iteration, this is the value taken for the fault, and this is for the aquifer volume, and so on. So you see it is changing with time based on evolution strategy method. And in the bottom, it will tell you that the best iteration is iteration number 32. What is the case name? SNARK HM47. So the best result is case number 47, which has the fault transmissibility is 0.4 and the aquifer volume is, I think, 1, 2, 3, 4, 5, 6, 7, 8, or 7, 10 to 7. If we look at the results, we will go to result charting. We will check the case, initial base case, again, which for this well, and this is the pressure. You remember this curve? It is mismatching. Now let's look at the results after assisted history matching. So I will check the optimization cases. You see it has gave me 50 results, and you can see here, and the best case is 47. So if I select only 47, let's search for that. This is 47. You see it has gave me a better history match, or the best history match between all the cases. So imagine that you have only 2 parameters, and each parameter has 5 ranges, and you gave 50 samples, and it was in this quick and fast. Imagine in the reality, you need to do this one. It will save your time. It will give you accurate results, and it will help you in your history match process. So this is the idea of assisted history matching. It uses a tool. You will set parameters, ranges, and you will give a start and end point, and you will ignore the not affecting parameter and control the affecting, and it will give you results. If I want to see the water, it should be also better, but not the best, because we didn't control the critical water. So here is water cut, split by property. Let's take a well with water here. So you see here, initially, oh, this is the water cut observed. Initially, this is the brown line. After matching, it has better, but you need to work more on water. Now you fixed your pressure. You need now to fix your water. And fixing your water, as I told you, is based on, thank you, Abdullah. And you need to fix your water. Here, your water is delayed. So as I told you, one of the parameter you need to change is the critical water saturation. Your current critical water saturation, just to give you quickly a view, is here. Let's see which case was used in the function. Okay, snark, skal. This one. This one was used. Tamam. So if I open spreadsheet, so this is your critical water saturation, 0.22. The last saturation at which the water is immobile. What you have gave here is higher number, so you need to reduce this number from 0.22 to be less. And that's it. Thank you for listening. I hope you enjoyed this topic. Please let me know if you have questions. Let's discuss. Otherwise, this is the end of the lecture.
If you
Any
have any
question?
questions, please write it in the
Please,
chat box
yeah, raise hand
or
or
raise your
chat
hand.
box. Thank you, Ahmed. If you have a question, either raise hand or write in the chat. Eddie is asking if we can have a record.
Yes,
How you
yes,
will share it,
there will be a record on the YouTube channel, so keep up with
Okay.
it. There is any questions? There is no
I think
questions. We can end it here.
you can stop the recording.
Yes, I will.